Hi, everyone. So, we're going to talk about water and sort of a big picture, which means that we will come back to each of these subjects in more detail. This is just sort of how we're going to kick off our water unit, is with sort of the big picture. Uh, Basically, why do we care about water? Why are we going to spend the next 6, 7 weeks focusing on water? Well, it's one of our biggest resources, right? We need it to survive, and it can do so many things. And it's a great way to teach chemistry because we do so much with water. So, water covers about 75% of our planet, and most of that is ocean. So, if it's ocean water, that means we can't use it pretty much because it's too expensive to clean. So the desalination process is very expensive. So to do it on a large scale, like for a city, isn't feasible, at least not yet. There are some boats, like some really nice yachts that have their own like desalination system. Some cruise liners, stuff like that, that have a desalination system. Uh, so it is possible, and we do it on a small scale, but to um, do that for a whole city, it's just not cost effective, which is why we haven't gone that route. So that's why we consider that 90, and actually that number is going up. The 97.5 that's ocean water, that's going up with ice caps melting. We have water levels rising, which means that some of that fresh water is entering the ocean, and that number is going up. So we consider that unusable at the moment for like life sustaining stuff. So that means 2.5% of all water on the earth is fresh water, and that means it's potentially usable. Of that 2.5%, so if we take that and think of it as okay, 100% of our fresh water, 70% of it is frozen. So it's either frozen on the top of mountains or it's frozen on in like icebergs in the ocean. So the icebergs in the ocean is what's melting because of global warming and increasing that ocean percentage. The ice caps on the mountains, as they melt, we do use those. I mean, that's why we have like rivers and dams and stuff like that. We do take water from that and clean it and use that as city water. Definitely, it's not just rain. Um, so some of that frozen ice as it melts, we do use it, but if it's frozen, we can't really do much with it. So again, a lot of it's frozen. So about 30% of that is what we actually can use. Um, it's groundwater that we have access to, either in the form of rain or streams or whatever. It's something that we can draw from, that we can clean. So that 30% of the world's total water, that's like 1%. 1% of the world's total water is what we actually can use. About. And then if we consider that 1%, 100%, most of it is used for irrigation. So like crops and farming and stuff. The other portion of it is used for industry, like factories. And then what we use for domestic use, like in our homes, like for drinking, for showering, for brushing our teeth, stuff like that, that's less than 1% of that 1% of water that's actually usable. So we actually use very little, like we're the smallest percentage. But that's why in California we get stuff like droughts, and we get stuff like people saying like we need to conserve water. It's because we can't really go without irrigation. We can't really go without industry. Obviously, we can't go without home use, but we can get back in the home. And so during drought times, that's what they try to focus on because it's something that everybody can do and everybody can pay attention to, shorter showers or whatever. So that's like the big picture of water. So why do we care about water so much? Like, why is it so necessary? Well, one of its major properties, these are all sort of like unique to water, all the properties we're going to go through, but it's a good solvent. It's one of like our few liquids on the planet that we have an abundance of that is actually a good solvent, so can dissolve many substances. So obviously it dissolves things like minerals. That's how we get ocean water, right? Is because it's dissolving salt. But it also can dissolve ions. I mean, it dissolves substances to make ions. Therefore, we have we can like conduct electricity through water and stuff like that. It also dissolves gases. That's how like fish and things that live in the ocean can breathe. It's because they're taking the oxygen out of the water. That's also like how we get soda. Is the carbonation that's in soda is carbon dioxide, which is a gas. We've just dissolved it into the liquid, which for soda is mostly water. It's water and sugar. Um, so that's unique to water. Not many substances can dissolve so many things. The density of water is one. Its maximum density is at 4 degrees Celsius. So 4 degrees Celsius is when water is liquid. At 0 degrees Celsius, it becomes a solid, and then at 100 degrees Celsius, it becomes a gas. So at 4 degrees Celsius, it is a liquid. It's very cold liquid, but that's when we get the maximum density of exactly 1 gram per centimeter cubed. So gram per centimeter cubed. So that's mass per volume. So as the volume gets smaller, so that's a denominator getting smaller, that's going to increase the density. So usually when things freeze, right? If you think about it, like gas can fill up a whole room and then you condense it and make it a liquid, right? So now it's a smaller area, and then you condense it even more and make it a solid. That is, and every time we condense it more, the density is getting higher and higher because it's the same mass, but in a smaller amount of space. So the density is going up and up and up. That's true for all other substances except water. Water, it can be a gas, it can fill a room, right? Water vapor. And then we cool it down and it becomes a liquid and it gets smaller. But when we freeze water, when we make it into a solid, it expands a little bit, not a lot, but a little bit. And when it expands, that makes the density less, right? Usually things are getting smaller, so the density is going up. But when water is a liquid and then it turns into a solid and gets a little bigger, it makes the density go down. So that's what you see here on this slide is the density of water is 1, but why does ice float in water then? Why doesn't ice stay suspended if the density of ice is also 1? It's because it's not. The ice got a little bit bigger, therefore the density got a little less. You can see the density of ice here is 0.91, which is what you see in that picture. Because it's very close to 1, it's floating right at the top with most of the iceberg underwater, but a little bit peaks out because the density of ice is less than the density of water. Therefore, it floats. If you have a density less than 1, it'll float. If you have a density greater than 1, it's going to sink. So you're going to see that in your lab on Thursday as you put things in the water. It's either going to float like really on top of the water. Like if you get something like styrofoam, it's not really going to be in the water at all. It's going to be mostly on top of the water. That means it has a really, really low density. If you take something like a rock and you put it in the water, it's probably going to fall really fast to the bottom. That means it has a really high density. If you put something in the water and it floats down slowly, that means it has a density greater than 1, but it's probably pretty close to 1, which is why it went so slow. If you put something in the water that is like you see in this picture with the iceberg and you have some sticking out and some below, that means you're also probably pretty close to 1. Because some is sticking out, it's probably less than 1, but it is still probably pretty close. So those are the things you're considering in your lab on Thursday is, did it sink? How fast did it sink? Did it float? How much of it is underwater if it does float? And you're going to predict densities based off of that, knowing that the density of water is 1. So another thing that the density of water is different than everything else is when it freezes, it expands, which that causes corrosion. So corrosion happens when basically it rains like somewhere where it's going to get below 0 degrees Celsius or 32 degrees Fahrenheit, right? When it freezes, so states maybe like Minnesota, that's a good example, like basically anywhere where it snows, those places are going to have more corrosion like in their streets and stuff than other places will. This is also why mountain ranges change and stuff like that. But on a small scale, we think about like, okay, we have a crack in the cement. and it rains and water gets all up in that cement. And then at night, maybe it drops below zero or below 32 degrees Fahrenheit, 0 degrees Celsius, and it freezes. And that water that's in that crack is going to expand and it's going to push that crack a little wider open. Then maybe the next day the sun comes out and that water starts to melt a little and fill up that crack, right? The water's getting smaller, which means that you can fit more in that crack. So you get more water into that crack, and then it freezes again and expands a little more. So by the time winter's over, that crack that was like this in the fall is like this in the spring, and now we have to start replacing the streets. So if you go to places like Minnesota, literally every summer they are doing construction on the roads because they have to fix all the corrosion that happened over the winter. So that's something else that's unique about water. Most liquids don't do that. So most liquids don't cause as much corrosion as water does because they don't expand when they freeze. Most things get smaller when they freeze. Water also has a really wide range between its freezing point and its boiling point. Most substances, it's a significantly smaller range, but water has a very, very large range, which makes it great because as humans, we need water in its liquid form. On other planets, it's too hot, so water's constantly in its gas form, which means that we would have to create something that took water out of the air, cooled it down, and put it in its liquid form because that's how people use it. So if we were going to travel to another planet, that's the kind of stuff we would need to consider is how do we make the water that's in the atmosphere into a liquid? Or if it's a frozen planet, how do we make the water that's frozen on that planet into a liquid? So we're fortunate that water has such a wide range, but it's also what makes it very valuable to the earth is that it can get hot and it can get cold and all the water won't freeze and all the water won't evaporate. So freezing point and melting point are actually the same degrees. It's 0 degrees Celsius. It's just going the opposite direction. So we give it like different names. So freezing, if you freeze something, you go from a liquid to a solid, but that happens at 0 degrees Celsius for water. And if you melt something, that goes from a solid to a liquid. But again, that happens at 0 degrees Celsius because it's a point. It's a freezing point. It's a melting point. It's the same point. It's still 0 degrees Celsius, but you're going opposite directions. Freezing is liquid to solid. Melting is solid to liquid. It just gives you some conversions there on the screen. So 0 degrees Celsius is the same thing as 32 degrees Fahrenheit. In the United States, we do use Fahrenheit for temperature, but in science, we use Celsius, and a lot of places around the world, they use Celsius. 273 K, that K stands for Kelvin. It's not a degree. That's why there's no degree sign. It's not a measurement of temperature. It's more of a measurement of like energy or movement within molecules. And in order to get Celsius to Kelvin, in order to convert, we just add 273. So at 0 degrees Celsius, we have 273 Kelvin. Boiling and condensation is the same thing. Boiling is going from a liquid to a gas, then condensation is going from gas to liquid. So again, it's the same point, just opposite directions. And for water, that happens at 100 degrees Celsius, which the equal for that is 212 degrees Fahrenheit. And if I wanted to convert 100 degrees Celsius to Kelvin, I would add 273. So that's how we got 373 Kelvin. Water also has a high surface tension. Most liquids don't have a high enough surface tension, so they can't create things like drops. Water can. So that's how we get rain, is because water sticks to itself and gives it like raindrops. That's also how sometimes you see like bugs floating on water. It's not because they're less dense. It's because the surface tension of water is very, very high. We're going to do a couple of surface tension activities. I don't know if you're going to do them at home or if we're going to do them in the classroom. It kind of depends if we're back in the classroom in October. But we will do a couple of activities where you see how surface tension can hold some things up. When we dissolve something in water, we call that a solution. We have many types of solutions. So we have a homogeneous solution, which means that it's uniform. It means it's the same from the top to the bottom, that if I take a sample from the top of my water mixture and a sample from the bottom, it's going to be analyzed exactly the same way. It's going to have the exact same stuff. So salt water, like ocean water, whether you take a sample from the top of the ocean or the bottom of the ocean, there will be the same generally the same amount of salt because it's a solution. It's a homogeneous solution. Snapple's in that picture. It's a decent example, like a juice, like any kind of like a Kool-Aid or something, just because it's uniform from top to the bottom. Heterogeneous means it's not. It means it's separated. It separates two ways based on the size of particles. So either it's a suspension or a colloid. A colloid has small particles, and then a suspension has big particles. Therefore, suspensions separate really quickly, whereas colloids separate a little bit slower. So something like Italian salad dressing is one of the best examples of a suspension, because if I take the Italian salad dressing and I have to shake it up, so I mix up all the herbs and oil and water and stuff, and then I put it on my salad and I put it down, and then my brother walks up 5 minutes later to use the Italian salad dressing, he has to shake it again because it's already separated. Those parts were so big that they've already separated. A colloid takes longer. So milk is a good example of a colloid because there's fat in it. So if I use like milk in the morning, and if you open the fridge and like carefully open the fridge, and if your milk has to have fat in it, but if you carefully open the fridge and unscrew your lid and look inside at the milk, you might be able to see like a little foam layer on the top. That's because after a while the foam separates. I think a better example, one that most of you have experienced, is like ketchup. If you use a ketchup bottle that's been sitting in your fridge like overnight, you have to shake it first. If you don't and you go to dump it out, like there's this like watery, yellowy stuff that comes out. That was oil that was in the ketchup. And if you don't shake it up, that's going to come out first because ketchup's a colloid and it separates. But if I take the ketchup out and I shake it and I put it on my hamburger and then I set it down, and 5 minutes later my brother walks up to put ketchup on his hamburger, he doesn't have to shake it again because it doesn't separate fast enough. So that's the difference between a suspension and a colloid. Is a suspension separates quickly and a colloid separates slowly. But those are basically the two main types of mixtures, homogeneous and heterogeneous. That's all I have for you today. Please let me know if you guys have any questions, either in email or in the discussion. And have a great day.